Cool. All right. So today what we're going to do is this kind of it's an Amber Alert. Are you guys getting Amber Alerts? Is that... We got one at like 1 a.m., right? And it just jolted me awake. And I actually, there's a way you can go in your phone and turn Amber Alerts off. I don't know that that's necessarily like a societally good thing to do, but like I was just done with it, and so I did. Anyway, today we're going to continue something that we sort of started hinting at when we started the finite difference work 2 weeks ago. And we're going to continue it, and this sort of brings us into the sort of second assignment, Jupyter Notebook, that we'll be doing on kind of zero dimensional, or kind of what's referred to as box models. And we're going to do this in the context of the actual model that you will be kind of looking at for the assignment, the assignment notebook, and I'll email this out so that it's all there for you. It's on the GitHub site already. You can access it and actually start, using it. And so my plan is Wednesday we'll actually kind of go through the example notebook, and you can start the kind of homework notebook in class. And because we'll sort of extend class, you may actually be able to sort of make a good dent in progress towards finishing that notebook in class. But what I'm going to do today, and what we're going to do with a lot of these models going forward, is sort of start off with more of the kind of scientific or engineering description of the problem that we're actually going to be solving. And I hope that did that trigger my... Okay, it's still recording. What that does is sort of helps us kind of understand the physical underpinnings, or biological, in this case, ecological underpinnings of the problem that we're actually trying to solve. It will also allow us to sort of examine what we already know or suspect about the system, or sort of look and try and understand what the math actually tells us about the system, and especially when it comes to what we'll refer to as parameters of these models, right? The kind of the things, the numbers that are fixed in the model that we need some kind of estimate of, or we need to calibrate them using real data. We'll talk about what intuition can be gained by just kind of looking at those parameters, what their units are, what those units tell us about kind of what they do to the particular system. Okay, so the topic today is September 9, 2024, is 0D or box models, okay? And we'll maybe kind of look at a couple, but I do want to kind of start off with the one that is in the sort of problem set, right? And we'll start off with an easier version of it, and we'll start off with sort of a more complex version of that as well, right? So in this case, the example model that we want to look at, or system, I'll say system, example system, is the global carbon cycle. And there is a lot that we are going to abstract away in this kind of very simplified version of the model. We will make a note of those things that we are simplifying away, but I'm not going to kind of, we'll maybe also spend some time discussing how we might treat those, right? And generally the way that we start off building this model will be the way that we build all models in this class, which is to start as simply as possible and then kind of start to add in complexity to our model. And then, when we get to a point where we can't add in complexity that we need to the system, right? And at least the way that it's framed, right? There's some process that's missing, and it's really important that we represent that process, but there's no clear way to be able to represent that process in the model the way that we framed it. We'll ask ourselves whether or not this is actually the right model for us to use, okay? And that's a process that you're going to go through time and time again, right? You'll start with a simple model, you'll add complexity to that model, you'll keep adding complexity to that model until you get to the point where you're like, well, I really feel like I'm kind of dancing on one foot, you know, like jumping on one foot, rubbing my stomach, patting my head in order to represent this particular process that's really important, and I need to take a step back and sort of really ask, like, is this the right model for me, okay? So the first thing that we want to do, I'll defer to my engineering students in the audience, which is anytime you're given a problem that you're supposed to be solving, like on a problem set or in a lab, right? What's the very first thing that you're taught to do as an engineering student as you go about solving that problem? Like in statics. Free body diagram, right? Or some kind of visual depiction of the problem, right? And for my geoscience students, or those that are not familiar with what a free body diagram is, right, is it's just a way of like drawing a picture of the system and kind of accounting for those things that we know, right? Those things that we don't know, right? That we're trying to figure out, what do we know? What do we need to solve for? Right? It's exactly the same thing that we're going to go through with this model, right? So I'm going to do this as very much as a box to the system, right? And for now, our model is only going to have two reservoirs of carbon in it, right? One that is related to what we will term the biosphere, right? So we'll have a box down here, right? And this will be the biosphere, right? And we will label the carbon in the biosphere as C sub B for carbon in the biosphere. And then the other reservoir that we will have is the atmosphere. Right? And how might we label the carbon in the atmosphere?
CA.
Yeah, C sub A, right? It's as easy as it sort of sounds, okay? So before we go any further, right, like let's think about, let's just take stock of how unrealistic this representation of the Earth's carbon budget might be, right? So let's just make an account of like what reservoirs might we be missing, or how are these reservoirs incomplete? Okay. All right, so let's just make a list here. Who wants to sort of volunteer, right? If this is my representation of the systems, these are the reservoirs, right? These are the carbon stocks. We're not talking about fluxes yet. We'll get to the fluxes in just a second. But if we just look at these two reservoirs, what are either some reservoirs that we feel like are either missing or reservoirs that perhaps are incomplete, right? Or represented in a very perhaps overly simplistic way?
Hydrosphere?
The hydrosphere, right? So yeah, so we're missing the hydrosphere, right? And so where might carbon be stored in the hydrosphere?
Oceans?
Yeah, like in the oceans, right? Like there's carbon matter in the oceans that's not biomass, right? There's dissolved inorganic carbon in lakes and rivers and streams, right? That is also in the hydrosphere. It's not biomass, it's inorganic, right? It's fixed in a form that's not usable by the biosphere, so therefore it's right. It's yeah, it's not part of the biomass, but it's still in the hydrosphere. Okay, where else are we potentially missing carbon? My geologist should know this, right? Where would where might like Mark Schmitz come in and criticize these reservoirs?
Lithosphere?
Yeah, right. So we're totally missing the lithosphere, right? Which I can't remember, but arguably is right like one of the larger reservoirs. It just so happens that the turnover times, right, the residence times of carbon in the lithosphere are like much, much, much higher than they are in the biosphere and atmosphere, right? So that might be one reason we don't represent the lithosphere. What about this biosphere box here, right? What are some ways that maybe like oversimplifies the problem? Like what comprises the biosphere? Presumably that's living.
Plants.
Yeah, so yeah, unpack that a little bit more. So like there's clearly, right, biospheric carbon in plants, but where else is there biospheric carbon? Animals, yeah. No, that's true. Yeah, animals. Okay. What are the plants living in?
Soil.
In soil, right? So we would consider that kind of like maybe non-lithospheric, even though it's, technically part of the crust. But yeah, so our representation of the biosphere is maybe missing complexity. That's important, right? And how might we know or sort of think about that, right? If you look at if any of you remember or have seen, right, the CO2 concentration is recorded by the station at the top of Mauna Loa in Hawaii, right? Like you'll see that clearly there's a big trend upwards, but there's also kind of this annual cycle to that carbon dioxide concentration. That's actually representation, right? So that measurement is actually meant to be a recording of this carbon content, right? So it's recorded in parts per million. If you integrate over the volume of the atmosphere, in principle, you get an estimate of the total amount of carbon stored in the atmosphere. But it has these squiggles, right? And what do those squiggles represent? Like when, what are we told or what do we strongly suspect about the squiggles in the carbon concentration at Mauna Loa?
Is there phenology of things?
That's right, exactly, right? So it turns out the northern hemisphere has way more landmass than the southern hemisphere, right? And because of that, the northern hemisphere greens up in the northern hemisphere, the boreal spring, right? It's very productive, and then it senesces in kind of the boreal fall, right? And that's when carbon dioxide concentrations go up, right? Because plants are less active. So, we're often told that we can see, right, the northern hemisphere basically breathing, right, on an annual basis. And so, right, we would suspect that we're probably with this simplistic representation of, hey, just a biomass, right, and a whole biosphere where we're missing, living carbon in the ocean, right? So the ocean actually does tons of photosynthesis. There's lots of photosynthesizing things in the ocean, right? We might be missing some really important nuances of the carbon cycle that are important, right? But for now, we'll stick with this kind of two reservoir representation of the atmosphere, okay? So now what we want to do is account for or ask, right, how are these two reservoirs linked to one another, right? Like that is, how does how does carbon get from the biosphere to the atmosphere, and how does carbon get from the atmosphere to the biosphere? Okay, so let's focus on one of these directions first and ask the question, okay, what about this arrow here of carbon going from the atmosphere to the biosphere? Maybe I want to, wish I could, let's undo that. And to draw a stronger hint, I'm going to color this in green, right? Okay, this arrow here. This is the arrow that represents the flux of, right? So this is the flux of carbon from the atmosphere to the biosphere. What is likely one of the biggest parts of that flux? We just talked about it a second ago. Zoe. Plants. And what are plants doing? How do they acquire photosynthesis, right? Yeah, we're probably not biologists in here, right? So this is the process of photosynthesis. Right? There's probably other ways that carbon gets from the atmosphere to the biosphere. But photosynthesis is probably like the very largest of all of these, right? And that includes photosynthesis. In our model, that would include photosynthesis of terrestrial plants and other things too, like, archaea, mosses, and lichens and stuff that do photosynthesis, but we don't think of, are not technically plants, right? And microbes in the ocean that are doing photosynthesis, right? So this includes all of that, right? That's all of those organisms doing photosynthesis, okay? Okay, now the other direction, so that's probably it, right? Is probably this, we'll call this F, and the notation I am going to use here is A sub A, B, right? So that is the flux from A to B, the flux from the atmosphere to the biosphere. Okay, now let's think about fluxes the other direction. Okay, so I'm going to label this now F sub B A. That is the flux from the biosphere to the atmosphere, right? And I'll just write that here in text, the flux of carbon from the biosphere to the atmosphere. Okay. Again, this is a perhaps ecological or biological nuance, but what are the ways? In this case, there's a couple of different ways that carbon gets from the biosphere to the atmosphere. One should be acutely evident right now in this past weekend, right? So how do we get carbon from the biosphere to the atmosphere? What's that?
Brief.
What was that again?
Brief.
Brief?
Yeah, from human.
Oh, breathing. Okay, yeah. Yeah, so that I guess that technically is true, right? So we take carbon that is stored in our cells and we respire it, right? So that's one source. It's probably small relative to the ones I'm thinking about, but yes, that is one flux of carbon from the biosphere to the atmosphere. Wildfire, yeah. So certainly like biomass burning, right? Is a big one at the moment. Okay. Yeah, that is an important flux. The other one, right? So, getting back to that idea of respiration that we do, right? So respiration is, right, is I don't want to get into too much biology here, but the process of, right, we think of respiration as being a byproduct, right? The things that we respire, CO2 in particular, right? We respire that, and that's evidence of our own metabolism, right? So the more you metabolize, the faster your metabolism, the faster you respire, the more CO2 you produce. If you go and exercise, right, it gets your heart rate up, you're metabolizing more quickly, right? Your body is taking energy that's stored in sugars and fats, right? And it's converting it into energy, into what's called ATP, which is what drives kind of motion in the cells. But in order to do that, it produces CO2. So the question for you is, do other organisms do something similar? And the answer is yes, right? So I'll just cut to the chase. So plants respire, right? Microbes in the soil also respire. The processes are actually sort of somewhat similar, right? Like so plants also produce like ATP, right, and they're doing that to do things like grow, right? And those of us that work in kind of the ecological sphere talk about things like maintenance respiration and growth respiration, right? That is the respiration, the metabolism we have to do in order to grow, right? Whether that's a tree or whether that's your bicep, right? There's a certain amount of respiration that is required, a certain production of CO2 and release of CO2 into the atmosphere that is required to grow a plant or a bicep or a colony of microorganisms in the soil. So we will generally call this ecosystem respiration. Okay. And again, those aren't the only things, right? We're missing decomposition, right? So when plant organisms die, right, they decompose. You could argue that that's actually a form of respiration because it's other organisms that are doing the decomposition. They're eating that material and producing their own CO2 to live, right? So we'll kind of assume that flux, right, that process is lumped in with this ecosystem respiration. So that seems like the kind of two big things that we need to worry about, right? So you can set the biosphere on fire, right? That will release CO2 through combustion, or it can respire, right? The plants, the microorganisms, the fungi can all respire, okay? So that is probably fine for now. Are there other fluxes? We might call them exogenous fluxes. They maybe bring in, arguably, the lithosphere. I'm giving you very strong hints at the moment, but are there exogenous fluxes into either one of these two pools, these two reservoirs of carbon that we might think about needing to account for? Aman, I see you shaking, like nodding your head. Fossil fuel emissions, right? So exactly. So we can think about, right, that as what's the most appropriate place to put that flux? Like, what is that? Like, if you had to use a word to describe what a fossil fuel emission is, like, how does that fit into our model?
Sort of flux of carbon from lithosphere to atmosphere.
Exactly. Yeah. So what we are doing is we're actually mining, right? We're mining. So we will call this the flux. We will call this of AE, anthropogenic emissions, right? Anthropogenic anthropogenic emissions. Okay. Right, and that literally, like, I'm not going to connect it to a lithosphere here now, right? But that's effectively like what we're doing, right? When we burn fossil fuels, we either dig coal out of the ground, we sink wells into the ground to extract either gas or other hydrocarbons. We refine those into things that we use for fuels, right? And then we burn them. That burning results in, right, an emission of carbon in the form of CO2 and methane from someplace. It's you can think of it as exogenous in this model, right? But it's a flux into the atmosphere. Okay, so now let's kind of move one step into the math, right? So what we're going to do now is we're going to set up a budget equation, right, for all of these budgets, and make sure that all of the terms balance with one another, right? Make sure we're not missing any fluxes or any reservoirs. Okay, so next what I want to do is, and we'll label this, right, like, so our system diagram. Right, and now what we want to do is we want to perform the mass balance. Okay? All right, so if we go back up here and we look at our two reservoirs, right, there's kind of what we would call what we would term state variables, right? Two variables that describe the state of our system, two things that might be changing through time, right? So think about this as that, like, this is when we go back to that analogy of the bank account balance, right? Like the balance in your bank account is the state variable. That's what you're tracking through time, and you're tracking how that changes as a function of how much money you make versus how much you spend. Right, so each of these are like a different bank account that are coupled with one another, right? The red arrow here and the green arrow here, couple with one another. So what I want to do is first, and we'll color code this with the arrows as well. Let's do this in the absence of that anthropogenic term. Let's neglect humans for now. Let's say that we're doing this as a kind of paleo model, right, or a model on some distant planet that we have reason to believe has a biosphere, but no higher organisms that are mining fossil resources and burning them, right? So if you remember, right, what we did is we talked about modeling or keeping track of the change in our bank account balance with respect to time, right? So let's start with the atmosphere. Okay. And how do we express the rate of change of carbon in the atmosphere as a function of time, or with respect to time mathematically? What does that look like? Exactly, yep. So it's just the derivative dc sub a with respect to t, right? So that is the instantaneous rate of change. This is the rate of change in Ca with respect to time. Okay? Okay, so let's do the mass balance here for the atmosphere. And again, we're going to neglect, right? We're going to ignore this anthropogenic emissions term for the moment. But what, right? So again, this is kind of just debits and credits, right? So income versus expenditures. So income, how is the atmosphere, quote unquote, earning carbon? Which of these terms here tends to increase the amount of carbon in the atmosphere? FBA, that's right. And that's in red, so that's the flux of carbon. BA, okay? So, and the sign in front of that is positive, right? This tends to increase, right? The flux of, this tends to increase the carbon amount in our atmosphere, right? Okay. What is the expenditure term? What is the loss term? FAB, exactly. FAB, right? So we'll label these. This is flux from biosphere to atmosphere. And this is flux from atmosphere to biosphere. Okay? Yes?
Why do you have a plus sign out front of FBA?
I only have that just to be exceedingly explicit that that term increases. It's not negative,
Right.
and I'm negating it. It's that it is a positive
Okay.
term. So, yeah.
Just making sure.
Yep. Okay. Now what do we need to do? We need to do that for the biosphere, right? Oops, let's undo that. Okay, so in the biosphere, okay. Similarly here, right, it would just be dC, the change in carbon amount in the biosphere with respect to time is equal to, now if we go again and look at the biosphere, in this case, how does the carbon amount in the biosphere change? How does it, I'm sorry, what causes the amount of carbon in the biosphere to increase? Which of these fluxes is the positive term, the income?
The green one.
The green one, yeah. So FAB here is positive. FAB, right? And the negative term is the opposite, right? So FBA is the loss term, right? That's the respiration and biomass burning, right? So this model hopefully makes intuitive sense, right? If we're tracking the carbon in the biosphere, what's coming in is coming in through photosynthesis. What's leaving is leaving through ecosystem respiration and through biomass burning. And if I'm in the atmosphere, right, what causes me to lose carbon in the atmosphere is all these plants sucking it up in the biosphere. And what causes me to gain it is a bunch of plants that are either burning or metabolizing and producing a bunch of carbon. Carbon dioxide in this process called respiration, okay? So now, right, so what's interesting about this model is that, right, these two reservoirs are very tightly coupled with one another, right? They share fluxes, right? That's not what I want to do. Right, they share fluxes that are, let's see, where's my pointer on this thing? We've changed it. Okay, never mind. So they, maybe it's over here. Nope. Okay, I'm gonna have to figure out how to point on this. Right, so they share the same fluxes, they're just switched in sign, right? And there are no other fluxes, at least, right, in the way that we've posed this model with respect to these two fluxes, these non-anthropogenic fluxes, right? So this system will kind of continue on, unforced from one another through time, and will likely reach some kind of equilibrium between the biosphere and the atmosphere, right? What will cause it to be in disequilibrium is if we account for what? FAE, right? And FAE is the anthropogenic emissions, right? That is a forcing to the atmosphere, right? And it is not a forcing to the biosphere, right? So it would be the only sink or source term in this model that's exogenous, right? And it's only applied to the atmosphere. Okay, so that's a conceptual representation of the model, right? And it's sort of a statement that's like, okay, well, maybe I could have, right? Like I could have given me long enough, right? Might be able to reason this with even like a fifth grader or something that's like, okay, here's your bucket of biomass. Either you can photosynthesize or burn it, right? If it's my son, then he'd be like at it with a lighter, right? But, but this is a pretty intuitively understanding model, but can we, right, how would you go about translating this into a model, right? Like what is the way, how would we even go about translating this into a model at this point? Like if I said, okay, write this up in Python and in a Jupyter notebook and turn it in, what would be missing? Could you solve this? Just a simple yes or no at this point. It's okay to say no. I couldn't, right? I couldn't, and the reason why is that, right, there's no relationship between these fluxes, FAB, FBA. FAE is just an external one that we would just be given a number, right? Like the Energy Information Administration would tell us like what cumulative emissions are in gigatons per year, right? And we would include that. But otherwise, right, I don't know how to represent, like, is this flux is FAB just a number that we get from somewhere, right? Or doesn't it have to relate to the amount of carbon in the biosphere, right? Okay. And similarly, like, yeah, doesn't right, like, doesn't the amount of carbon that's emitted from the land surface depend on one of these carbon fluxes? And so the answer is we can't yet turn this into a numerical model because we don't have a prescription for how these fluxes actually relate to the thing that we're trying to capture, right? This amount of carbon in the atmosphere and in the biosphere, right? So what we need is we need, and the term I'm going to use is parameterizations that describe how the fluxes relate to carbon storage in the atmosphere and biosphere. Okay. All right, so I said we were going to start simple. We're going to start very simple, right? So let's start with this flux from the atmosphere to the biosphere, and I'll keep using green. So FAB right, what we will say is that, well, I think what are the dynamics I'm trying to capture? Like, what am I trying to capture here? Well, Right, that is generally, okay, so, my geologist in the room, or anybody that's watched Jurassic Park, right, like, when in Earth's history and why did we have, like, these plants in the tropics that had, like, leaves that were as big as this room?
Cretaceous.
Yeah, right, and what was special about the Cretaceous?
Plants dominated everything on land.
Yep, and what were CO2 concentrations in the atmosphere? Were they higher than present, or?
The oxygen levels were high.
Oxygen levels were high, right? Well, that was because plants were producing a lot of oxygen. CO2 levels were higher too, right? Like, so generally what we're trying to sort of capture is that, like, when there's more carbon in the atmosphere, right, and this is true down at the level of individual stomata of leaves, right? Like, if you take a leaf, just a leaf, and you give it a CO2 rich environment, right, it's easy for that carbon to get into the plant cells, right? It just diffuses in through the stomata. So really what we want to capture is just to say, when there's more carbon in the atmosphere, our flux from the atmosphere to the biosphere will be larger, okay? So the way that we're going to prescribe that is say that there's just this coefficient K, A, B, right? And we're going to multiply that times the carbon in the atmosphere, right? Okay. Now, real quick, this gets to kind of what we can intuit about the problem just by looking at the model. Okay, is let's do real quick, right? So again, this is why I love having my engineers in here, because I was an engineer, and I appreciate that, like, right, a double check on whether or not the problem is right when you're handing it in, right, is whether or not the units are correct, right? So my engineers are grinning, right, that you always double check the units to make sure that what you're turning in, right, is at least like the right units. Like, that's a necessary but not sufficient condition. Okay, we'll stop after this, but and take a break. But okay, so let's say the units of carbon, right, for convenience are in something like gigatons, right? Gigatons of carbon. That's a mass of carbon in the biosphere or in the atmosphere. What are the units of this equation going to be? Right? There's a gigaton up here on top, and on the bottom here is time, right? So what's a reasonable unit of time we might be working with at, like, climate timescales? Year, right? So gigatons per year, right? So if our flux, and that means our fluxes have to be in units of mass per time, right? C is a mass, T is a time, right? So this will have units of time, right? So I'll draw it this way. So this will be in units of mass per time. This will be in units of mass. What will be the units of my K coefficient? 1 over time, right? Okay. So, that's super interesting. So when something's a unit of 1 over time, right, what if we take that number and we just do the inverse of it?
Frequency.
What's that?
Frequency.
It's like a frequency, yeah. So it's very similar to a frequency, right? And when you flip a frequency over, you get, like, right, you get characteristic time, right? Similarly, when you flip, right, something like this over, you get something that's also kind of a characteristic time. It would be called, like, the residence time, right? So this is just like 1 over the residence time, right? There's a couple of different ways to look at this coefficient, right? This coefficient, well, first of all, we can bound it numerically, right? Can this coefficient ever be less than 0? No. Yeah, it has to be positive. If it's less than 0, then that sort of, it doesn't make any sense. We're creating mass. We're violating, violating all kinds of laws in the universe, right? Can it be greater than 1? Yeah, no, it can't be greater than 1, because that would mean, right, like you can produce more than 100%, right, you can photosynthesize more than 100% of the carbon that's in the atmosphere, right? So again, if it's more than 1, we're also kind of inventing mass, which is not physically possible. So this is a number between 0 and 1. We take its inverse and we get some kind of residence time, right? A turnover time. How often does the carbon in the biosphere or the atmosphere turn over, right? And we can learn a lot about this, right, just by thinking about this, right? So, so if that number, if another way to think about that, if it has to be between 0 and 1, right, as a fraction of the amount of, in a single year, right, if this is gigatons per year, if this is 1 over year, I can think about this as the fraction of carbon in the atmosphere that's going to move to the biosphere every year, right? So we can think about it as a fraction or also sort of like as a percentage, right? So if this is like 0.04, I can say, well, usually every year about 4% of the atmospheric concentration is going to go into photosynthesis, right? So we can intuit a lot about our systems just by knowing the units of the system, right? And we could probably even like make reasonably good estimates, like order of magnitude estimates, just by kind of thinking through like orders of magnitude of the problem. Right, like probably this number in reality, right, if we're actually trying to represent the Earth system, like I'm just gonna wager a guess here and say that like the max I would ever expect this to be would be like 10%, right? Like, and even that would be maybe stretching it, right? Some global change ecologist might come in and be like, no, it's not 10%. But I'd be like, okay, but at least I didn't say it was 50%, right? So there's a lot we can learn just by looking at these. And these parameters, these coefficients, wind up being super important. So take like a 5-minute break, come back at 2:25. We're going to finish up, right? We're going to do the same exact thing for the flux from the biosphere to the atmosphere. We're going to line up all of those equations again and then look at how we go about solving these equations numerically. Okay? Okay, so let's do the exact same thing that we did for our kind of quote unquote photosynthesis term for our respiration burning term, right? So in this case, right, we're going to say that FAB equals K, I'm sorry, not AB, BA. The flux of carbon from the biosphere to the atmosphere is KBA times C sub B, right? And again, just to be a little bit repetitive and pedantic, we'll account for the mass here, or the units, and say that the units of our coefficient here should be something that has units of 1 over time, right? Years inverse or something like that, right? And our carbon will have concentrations of like gigatons, okay? And so we can think of KBA and KAB as being something like turnover times, right, or the inverse of turnover times of our system. Okay. Okay, so, right, these are just what we would call parametric representations of the fluxes, right? They give us a quantitative estimate of the flux. They're parametric because they have a parameter here, KAB or KBA, that we need an actual number for, right? And they now depend on, they multiply, right? It's just a proportion of some reservoir that's moving from one reservoir to the other reservoir on an annual or every time step basis, okay? All right, so what we want to do is we want to rewrite our budget equations inserting the flux parameterizations. Okay. So if we start off with the atmosphere, dCA dt, right? And all we have to do is go back up and look. So dCA dt is equal to FBA. FBA is just KBA times CB. So KBA times CB, right, minus FAB, and FAB is just KAB times CA. And dCB dt is equal to, right, again, this is sort of tightly coupled, so what comes into the biosphere is just our photosynthesis term, which is just this part, KAB times CA. What goes out as ecosystem respiration or biomass burning. That's just this term here, KBA times CB. Times CB. Right, and if I wanted to represent that anthropogenic term, here I would just need to add this FAE, right? And I could include that generically even when I'm modeling paleo world, because what is the anthropogenic emission term before people arrive on the scene? It's 0, right? So we could still include it numerically. It's just going to be 0, okay? Okay, so now this is getting closer to something that looks like we can solve it, right? Because everything is expressed either in terms of constants or in terms of the things that we're trying to estimate, right? And again, if this were, right, like this is a first order, right? So we only have terms that depend on the first derivatives of stuff, right? So if you took differential equations, this was known as a first order differential equation, right? It's linear. There's no, right? There's no dependencies on the derivative terms that are squares or not, right? Not linear, not more than 1 or less than 1. You didn't take DiffEq, don't worry about this. Right, so it's a first order linear, it's a full differential, it's a first order linear differential equation, and it's a system of equations because they're coupled to one another, right? You see here that CA actually depends on the concentration, or not the concentration, but the mass of carbon in the atmosphere actually depends on the mass of carbon in the biosphere, and vice versa, right? The mass of carbon in the biosphere depends on the mass of carbon in the atmosphere. So these two equations have to be solved simultaneously with one another, right? You can't decouple them, okay? All right, so how do we, right, so again, in diffie-q, you would do something like, well, let's guess some solution that looks like e to the x times sine x plus e to the x times cosine x, whatever, right? And then you'd find some analytical solution, right? And there are analytical solutions that we could look for, right, that kind of are end members of this system, right, which are sometimes useful. In the Slingerland and Kump text, like they provide a nice example of, you know, how you can find so-called asymptotic, right, so steady state solutions of this, right? So in the complete absence of humans or any exogenous forcings of carbon, right, how much would be in the atmosphere, how much would be in the biosphere, right? Those are maybe useful things, especially if you're looking at concentrations of carbon in, you know, fossils and rocks that you find, because it can help validate a simplistic model like this and get your turnover times, right? Estimate your turnover times. But we care about this kind of, we'd like to move forward, right? We want to do things like add, for instance, the anthropogenic term, right? We want to ask, okay, what is the, right, how quickly does carbon in these reservoirs stabilize as we impose some kind of emissions reduction scenario, right? We could have so-called negative emissions there, right? So CO2 removal to see what happens, right? What happens as we remove carbon from the atmosphere, right? So we want to solve this numerically, and we started off by using this sort of like finite difference term, right? So what I'm going to do is I'm going to divide these differentials into finite differences instead, right? So we're going to come up with a finite difference approximation for this. So using a finite difference approach, okay, so our dCA dt term, right, this just becomes, if any of you are actual mathematicians in the audience, I apologize. I'm going to say this is a full equals. This is not a full equals, but for us that are engineers and numerical modelers, it's close enough, right? So this is going to be CA at some t plus 1 minus CA at some time t, right? I'm using a superscript here not to denote an exponent, but to denote the time at which this happens, right? Divided by a delta t, which I'm going to choose. And I'm going to say that this equals, right? And I'm not going to include the anthropogenic emission term here now, so just for brevity. So I'll say that this is KBA times CB at time t minus KAB times CA at time t. Okay. So similarly, dCB by dt is going to equal C carbon in the biosphere at time t plus 1 minus carbon in the biosphere at time t divided by delta t, and that's equal to KBA times CA at time t minus k this should be AB. AB minus k BA times C sub B at time t. Okay. I've now turned this differential equation into like an algebraic equation, right? If I think about this, right, I could solve for, right, if I think about this sort of in forecasting mode, I'm interested in, right, you know, an algebraic equation, or, right, is an equation that we can rearrange all the unknowns or like the key unknown on one side with all of the knowns on the other side and actually just numerically turn a crank and solve for it, right? So the only thing that's different in any of these equations are the terms, right, that have the t plus 1 on them, right? Those are the special ones. And we can isolate those on the left-hand side. And in principle, if we can get numbers for all of the other things, solve for that unknown term, right? So solving for the t plus 1 terms, right? So I'm going to do this I get in trouble when I do this, so please, if I do any of the algebra wrong, the arithmetic wrong, call me out, okay? After I stop recording, I'll tell a funny anecdote of when I posted some code that got some arithmetic wrong. Okay, so, all right, so, you know, this is a straightforward equation to solve. And we'll talk about some intuition about what it means in a minute. But if we solve our term for carbon in the atmosphere, so carbon in the atmosphere at time t plus 1 just equals, and I'm going to use a parentheses here, so KBA times CB at time t minus KAB times CA at time t. This part is times delta t. And we have an extra CA at time t here. Okay, so, right, we can think of this here as just the net flux over time, over delta t, right? Going back to our bank account anomaly or example, right? If we think about our bank account example, if I told you like, hey, on balance, you're spending about $100 more than let's be positive here. You're spending about $100 less than you make every week. So what is your balance going to be in a month, right? The simple answer to that, well, I just gave you the net flux. It's plus 100, right, per week. And if a month is about 4 weeks, right, you would say, well, how much do I have in my account right now? That's this CA at time t. What's the net flux? Well, it's 4 times 100, and then delta t is just 1 month. Right, so it's just whatever you had plus 400, right? So that's the way we can interpret this finite difference equation, right? And so similarly for CB at time t plus 1, this just equals KAB times CA minus KBA times CB at time t, these are both at time t, times delta t plus CB at time t. Okay. Okay, so now let's just write down the exact things that we need to know in order to actually be able to calculate a number, right? I would posit to you there's 4, kind of 5, right? So if we wanted to turn this into a number, what are the things that we need? So to solve this, we need, what do we need? Just like shout out the variables. KAB, KBA, yep, CA at time t, CB at time t, and we need to know delta t, right? Okay, so these are parameters, right? These have special terms, a special name. In differential equations, if you took it, you already heard this term, but it maybe takes special meaning here, right? These are initial conditions, ICs, initial conditions.
Is the delta T part of that too?
No, it's not. Yeah, this is just choose for convenience. We'll talk about this more next time. Stability. Okay. All right, so as we wrap up class today, I want to set aside parameters because I want to make a bold statement here at the very end. This we will pick, right? This is a knob we have to control. Initial conditions, where might you get initial conditions?
Could be given in the data maybe, or
Yeah, just somewhere in the data, right? Like, asking ChatGPT, like, how much carbon is stored in the biosphere on Earth, right? Like, have ChatGPT come up with a number. Can you convert that into gigatons? Thank you. Right? We can get these numbers, right? There are people whose job it is to estimate these numbers. Same thing with the Mauna Loa thing, right? Like, we've seen the data that reflects the amount of carbon in the atmosphere. So these are initial conditions. We can get these, right? These are a little harder, but I want to suggest to you that maybe it doesn't matter. And why is that? All right, so right before the break, what did we do? Yeah, we were looking at what? The units, right? We're talking about things like turnover times, right? And we surmised that this has to be between 0 and 1. And it's probably like smaller. It's probably closer, like less than 0.1. Maybe like 0.01 or 0.05 or something like that, right? It could be expressed in terms of a percent. So if we got these numbers from, say, ChatGPT or Google or wherever, right, I would submit to you that you could actually, like, with just some reason, get a model like this up and running and get relatively reasonable answers for, right, what is the carbon in the atmosphere and ocean and biosphere, right? Atmosphere and biosphere, right? So you could come up with a model that shouldn't crash and should be reasonably well, do reasonably well, right? If you could get just these. So in actuality, you kind of need 2. This parameters we actually often wind up calibrating or fitting. We'll talk about that later in the semester. Okay. All right. Wednesday, we're going to actually code this up and use a notebook that already has this working. and this will be basically like the homework. We'll talk about like maybe a more sophisticated version of it. I think there's a more sophisticated version of it in the example code. So, okay. All right. See everybody Wednesday. And the cookies and coffee were already set up downstairs, so if you hustle. So the geosciences seminar is at 3. So, and anyone that wants to can come.
Yeah, Jerry comes for coffee and cookies all the time and then takes off, so you.
Yeah, that's right. Some of the faculty do that too. I won't name names, but.
Thank you.
All right.